Yes, okay, great. All right, so first of all, kinetics, right? Remember, it's kinetics are causing motion. So in chapter 1 to 3, we were just looking at motion. Now we need to find what is causing that. And then one of the equations that allows us to analyze kinetics is the linear impulse momentum equation. So for example, here there are two examples. One that are really enabling you to do real life analyzing real life situations, like for instance, decelerating or accelerating, as in example 4C1, or collisions, as in example 4C4. So then this video shows nicely example 4C4. By the way, this is found in this is found also in the website.
These dynamics carts and these masses. By having this cart start with an initial velocity and colliding it with a stationary cart, we're going to see how velocity scales when you add additional mass to the system. We're going to use Velcro to model an inelastic collision, and we're going to compare our initial velocity using these photo gates with our post-collision velocity using the same set.
In this experiment, we will be examining the conservation of momentum of an inelastic collision and energy loss as a result of that collision. To understand the collision, we will break our system into two times, one pre-impact and two post-impact. Prior to impact, our momentum is given to us entirely by cart A, as it begins with an initial velocity, here VA1, while cart B begins at rest. When we look at our system post-impact, we now have to account for the masses of both cart A and cart B. Because they collide in an elastic collision, they will have the same velocity, v2. Knowing this and working from our conservation of momentum equation, we can solve for the final velocity, v2, in terms of our masses and our initial velocity, which we will measure. Also, we can compute the ratio of the final velocity to the initial velocity in terms of the masses alone. Using kinetic energy, we can also calculate the percent energy loss of the collision in terms of simply the mass. We break this experiment down into 5 cases.
Okay, let me stop it here. So this is essentially what problem 4 was about, right? We had two masses, one hitting another one, and then we were taking a look what happened with the energy. What was the ratio between the energy before collision and after collision? That is you can convert that ratio in a percentage of energy lost, right? How much energy was lost by the collision. And then the other thing that they're doing here is how is the velocity or the speed changing as we increase the mass in our system. So these are two important pieces of information that these analyses give us.
Changing from equal to the mass of cart A to 5 times the mass of cart A. We will predict the velocity of the system post-collision and compare it with the velocity prior to impact. We will also calculate the percent energy loss for each case. To begin our experiment, we will first measure the initial velocity of the cart, 0.76 meters per second. As the test progresses, we will display the measured velocity post-collision and compare it with our predicted value. Mentally, note how the speed scales compared to our initial velocity for each test. Additionally, notice that these numbers generally are as predicted. While there is some experimental error due to frictional losses in the system, as well as the sensitivity of the equipment used to measure velocity, the predictions are met most of the time. As a result, we can see that our predictions are upheld and that velocity does scale with mass in an inelastic collision.
So I think, I mean, this is I like a lot that video because it shows, you know, an experiment. It would be very nice if we had a lab, but that is the type of experiment that you would go to do in a lab to test kinetics and see how it works. Now, what is the point of showing that? The point of showing this is that, you know, a collision is something that is complex, and the amount of energy, for instance, if you're working on a car or you are doing some sort of you know, tests for the army or something like that, there are going to be collisions involved. And while the car deforms and gets destroyed, that problem is complicated. The amount of energy that you are dissipating can be calculated directly from this, right? How that energy is then going into the formation of the car, etc. This is a different issue. But a first approximation is going to be given to you by this very simple but fundamental equation. Now, another interesting example that I like to do is this example of a paper that analyzed how mosquitoes fly on the rain. So have anybody thought about, is anybody from the tropics here? How can I stop it? Sorry, I'm trying to stop it, but I can't. Anybody from the tropics? When it rains, mosquitoes come out. It's horrible, right? Even here, right? But in the tropics, it's even worse. Or in Florida, maybe it's the same story. The south of the US. But it's pouring down. How are those mosquitoes being able to fly? I mean, it's really, it's a curious question. So these guys actually went on and started thinking about it. And the fight between the mosquito and the raindrop is very uneven. So mosquitoes are about 5 millimeters. The raindrop is about 5 millimeters, okay, the same size. But mosquitoes are far lighter, right? So imagine that, you know, okay, I'm 90 kilos, so 200 pounds. If 10,000 pounds come and hit me, I'm done, right? But the mosquito somehow is not killed by the raindrop. And then these guys are falling pretty fast, the raindrops, you know. 9 meters per second is about 36 kilometers per hour. So, you know, 20 something miles, 36, a little bit more than 20 miles per hour. So, you know, sizable, I mean, a super big mass that hits you at that speed should, you know, destroy you. So how do they survive? Anybody knows? Okay, let's see what the presentation tells us. Oh, this is a video. This is coming from a paper from, why is it not going? It's not playing for some reason. Okay, we'll have to, the video is not playing. Let me see if I can make it play on outside the, if I can play it outside the, over here. So you're seeing the video, okay? So what happens is this. Mosquito skin are hydrophobic, right? They are afraid of water. That's the literal translation from Greek of hydrophobic. What it means physically is that when a raindrop hits the mosquito, it doesn't break. What does it do? It bounces off, right? So if you think about what bouncing off means in terms of collisions, what does that mean? It hits you and then it keeps going, but it doesn't transfer too much momentum to you, right? So this thing that they were demonstrating about an inelastic collision, we're going to look at that more on Monday. But an inelastic collision is when something hits you and sticks to you, or doesn't bounce off too much. And there is where there is energy loss. And an elastic collision, when something hits you and perfectly bounces off, it's called an elastic collision. And what happens is when you have elastic collisions, energy is conserved. And the raindrop keeps all its kinetic energy, or most of its kinetic energy, and keeps falling fast, and the mosquito can keep flying by having this incredible adaptation. So it's pretty cool how this looks. Then let me just show you a little bit more. So, you know, there's a huge raindrop. It hits the mosquito, and then it doesn't break it. It just makes it fall a little bit. I mean, when it traps the mosquito, I mean, it's bad, but as soon as it lets it go, then it's okay. Now, this is the difference. This is the difference. If water doesn't bounce off, all that momentum that was coming with the raindrop, it's transferred to the mosquito, and that is what breaks you in the end. All right, I mean, I don't have too much time, but this is a paper on the proceedings of the National Academy of Science. So every professor in this world aspires to become a member of the National Academy of Science. Have you heard about it? I mean, it's probably not something you guys know about, but that is one of the, I mean, whenever Purdue hires Academy of Science member, then we go up in the rankings, right? Because these guys are really prestigious, etc. So this is a paper on the journal of that body, and the equations that they use are what? Conservation of linear momentum in the y direction. Why is that? Because simple doesn't mean trivial. When you can capture a complex problem with a fundamental equation, that shows that you understand the problem deeply. And this goes to what I said in one of the classes in the beginning. When engineers from industry come here and tell you, don't worry about you learning in university, it doesn't work, you know, we're going to retrain you. And I said, and I stand by that they are saying that because they didn't understand what we teach. It's true. Because everything we teach here is the fundamental. It's simple, but simplicity hides complexity. And actually, when you have a complex thing, what you want is to, you know, boil it down to the fundamental, to the minimum model that you need to explain a complex problem. This is that, all right? The fundamentals are conservation of energy, conservation of momentum, to second law. These are the fundamentals that you can use for any mechanical type of problem. So I always like to show these because it really shows, and it shows, you see, the change in speed when they are flying and they get hit, it scales with the mass. This is the same that we saw in problem 4C, 4C4, and in the previous example. Nothing beyond that. again, two masses that collide to one another. Okay, you have to measure it, etc. It goes more difficult, but in the end, everything is linear impulse momentum. So if anybody's interested, then I would show you a little bit more about this. Do you have any questions? No? So I hope that I convince you, please. Even if you think it's not going to be useful, when you understand it, you're going to find the utility. All right. So now let's get on with the class. Sorry. So we are studying linear impulse momentum equation. We went already through these, but it's another embodiment of Newton's second law. We integrate with respect to time, and then we get it. So we have discussed already these two quantities, impulse and linear momentum. Mass times velocity, and impulse is the integral of some force over time. And we know that it's a vector equation, and that relates changes of velocity with changes of time and the application of a force. Then I very quickly said that when you have a system of particles, you have some internal forces, but that internal forces don't contribute to the change of momentum. And then the homework that is due tonight, it's such a system of particles. It's just that one is on top of the other, as opposed to, this more abstract way of showing it. So which internal forces are there in the homework? So if I draw, this is a very simple system, but those normal forces are internal. So we don't need them, right? And then it also says that it's a rough surface. So that is going to lead to what? To friction, but it's internal. So at least for the momentum part, we should take the system as a whole, all right? So that should be your strategy when writing these free body diagrams. Now, let's do this conceptual problem. It's 274. Let's see if I can manage to solve this and solve the other one. So we have a block A, we have a cart A and a block B, and they have some masses, right? And they are connected by a spring. So there is spring there. So we have that the system is released from rest while the spring is being compressed. And we're asked to find what's the speed of the cart at position 2 when the spring becomes uncompressed. There is no friction. So let's just write the find. We need the BA2, right? Okay, so we do a free body diagram. So which strategy do I follow? Do I break up my system, or do I look at the system as a whole? So I keep my system together, right? Because it's quite clear that I will need to use work energy, right? Because we have compression of springs, we have changes in velocity or speed. And that also requires us to keep the system as a whole. But indeed we need also to do momentum, or we're going to find that it's going to be useful. Are there any other external forces applied to this system? You know, the surface is smooth, so we don't have any friction. So what can we see already? Do we have anything nice about momentum here? No forces in the x direction, right? So the linear momentum is conserved. So that's going to be useful. Now, let's do kinetics. So if we do kinetics, and I think that it's, again, and work energy is a little bit more intuitive for everyone. So let's start with that. So we do the kinetic energy in position 1. We start from rest, right? Release from rest. So it's 0. Potential energy in state 1, it's equals to the amount of compression that we had, right? We don't have a change in height, so there is no gravitational energy involved. Then on state 2, we have 2 masses. So the mass of, okay, the big mass is the cart. So this is the mass of the little mass, b squared 2 plus 1/2 big mass b a 2, right? 2 masses, there is relative motion between the two. And okay, I should say, is there non-conservative work somewhere? No, right? There are no forces that do non-conservative work. And then is there any potential energy stored in the system in state 2? No, because that's the point where we have the unstretched spring. Okay, so we can say then that the linear impulse work energy equation is giving us this k square, it's equals to 1/2 m bb2 square plus 1/2 capital M va2 square. This is our equation number 1. So what do we have? We have too many unknowns. Can we do anything about these unknowns? I mean, we have 1 unknown, 2 unknowns, and this unknown. Yeah, so of course, we need to use linear impulse momentum. No, we don't have species right there. Okay, so we use linear impulse momentum. So there is no external force in x, but I'm still going to write it. And then the initial momentum is what? Exactly. Because the initial speeds are 0 because it's released from rest. And then mass of the little mass in state 2 plus big mass of the cart in state 2. So then we get that the mass of the, let's solve for this one. I'm sorry, I'm writing quite bad today. It's equals to the big mass over the small mass, A2, negative sign, right? That's also intuitive. As we saw with the ball, they are going to move in opposite directions because one is transferring momentum to another. Okay. But we still, what's happening? The compression is given. Okay. So we have just two equations, two unknowns. So then we substitute there and that's it, right? Now, in here, there are a few things that we need to recognize. I mean, because I'm teaching linear momentum, I think that everybody can say, okay, yeah, we need to use linear impulse momentum. But how can we recognize that we don't need to look for some complex kinematics in our problem to find our second equation, and that we have to go for linear impulse momentum? It's not obvious, and I'm going to give you this time the answer quickly, but try to remember it. There is internal motion in your system. Internal relative motion, right? Can you notice that? This mass is moving relative to this cart internally. If you do your, what I call the control volume, you remember that? So whenever you have this internal relative motion, that's hinting strongly that if you have conservation of momentum, you should use it. Because otherwise you need to find some kinematics to find the relative velocity between block A and B. Do you see that? So this is a strong hint of the need of using linear impulse momentum there when you have these internal motions. Any questions about this? Okay, let me give you some more theory then that is going to really simplify your problem solving. So let's go to page 232. And this is not there on page 232. So you have to either take notes or maybe pay attention, and then you can watch the video and take notes when you watch the video later. So when can we have conservation of momentum? Let's say that this, what I call case one, is the block is at rest. So this block, the free body diagram, is going to be subject to these forces. Weight and normal force. But we can see, rather simply that the forces in the y direction are balanced, is static, right? And in the x direction, there are no forces, so we have 0, right? So the acceleration in the y direction is 0 because the forces are balanced. There are no forces in x direction, then the acceleration is 0. So the reaction forces in the x and y directions are 0. So then we say that the linear momentum is conserved. In which directions? Okay, not in all directions. Let's say in x and y directions. Right? So even if there are forces in the y direction, there is no acceleration, there is no motion, so then momentum is also conserved because the reaction force in that direction is 0, right? So that comes from the reaction force here. If that is 0, then the momentum is also conserved. Now, if we have that block, it's moving with some constant velocity, the situation is the same again. We only have forces in the y direction, but they are balanced. Excuse me. Sorry. And hence, we have also conservation of momentum, okay? So this is important to understand. It's not that forces are not there. Forces may be there, but they are balanced, then also momentum is conserved. And if there are no forces in that direction, then it's fine. Let me just ask you a question. What if I just, because this is going to come from Monday onwards, what if I look at the momentum in this, let's call it the E gamma direction? Will momentum be conserved on E gamma direction? In this particular problem? Huh? It will. And the reason because it will is that when you take the projections of the forces in this direction, you also get a zero there. Because the system is at equilibrium, it's not moving at all. All right? So we are going to start having to consider other directions apart from the Cartesian directions later. Gravitational forces. So when we have gravity, we need to pay attention about what's going on. So one way to do and deal with gravity is to take the system as a whole. And that means taking also Earth into account. And then gravity becomes an internal force. Now, this doesn't really work always, but I just wanted to bring this as a possibility. If you're doing, satellites, etc., you may even think about this in this way. But essentially, if you have something that is on free fall, then the momentum is changing. Why is momentum changing if you have something on that is falling? I mean, free fall is not changing because free fall means that you have terminal velocity. So you're moving with constant speed, right? But if you're accelerating while you're falling, no, you're always accelerating. If you have not reached a constant velocity, then your momentum is changing on that brief period of time. So gravity can be impulsive only for a short period of time. Now, springs are a little bit trickier. I think with gravity, it's easy. It's relatively simple to know whether it's changing the momentum or not. But with springs, so if you have springs here and you break up your system, you're going to have an internal force, the spring force. And then you say, okay, my momentum is not conserved because I have the spring force. But if you take the system as a whole, what happens with your spring force? It's an internal force. So it happens that internal forces, if we deal them in that way, then with springs, we can also get rid of it and it conserves the momentum. As we did with the cart. Do you remember the problem we just did? You guys on the back agree or don't like this? Yeah? Any questions? So is this momentum business easy, difficult? You prefer if we only learn conservation of energy? It's also cool, I think. And if you ever do something like, astrodynamics, momentum is so important because it's more general than conservation of energy. Anyways. All right. Or if you study, if you do like I do a little bit of bioinspiration and you look at why, how can mosquitoes bite you when it's raining or something, then you also use momentum. Okay, so let's do something that is going to help you for your homework problems also. 4C6, this is I always like this problem. It's one of my favorite problems because this is the type of problem that I can put on an exam and if you have not studied, if you have looked at other problems, it tricks you. It's a tricky problem. So we have, simple statement. Particle P has some weight, is released from rest, and it's sliding down a smooth rod, and then it sticks to block B. And then we need to find the maximum deflection of the spring that is attached to block B. And notice that block B has some mass. So we have a system released from rest, we have smooth rod, and we have the weight of each block, but in particular, block A has some mass. So looking at this problem, in an exam with the pressure, what would you start with to try to solve this problem? What?
Work energy to find the velocity.
Work energy, yeah, work energy. I mean, everybody starts with work energy, and then you can be very happy after a short period of time. Because, you draw your free body diagram, there is normal force before contact, during contact, there is, here, some force from the spring, etc. And then you say, okay, work energy. And I've seen, when we were proctoring the exams, I look at the students to see the approach of the problems and how they are thinking. And then I try to use that to then help the next generation not to make the same mistakes. So typically I see this. You see, oh yeah, release from rest. So energy, potential, kinetic energy in state 1 is 0. So try to, how do you say, enact with me the exam part. 0. Then potential energy. Okay, I look at this. What is the potential energy? Change in height, right? So mgh. Non-conservative work. Okay, smooth rod, normal force they do no work. So no non-conservative energy, right? Then in state 2, oh, I need to calculate maximum compression. Oh, I didn't write that. Maximum compression. So it means that the kinetic energy it's 0, right? Because all the energy has been transformed into compression and into potential energy in the spring. Okay, great. Work energy, and I get my solution. And 20 points. I mean, it's okay. Sometimes it's like that, but we need to take a closer look at what's going on. So what's wrong? Why don't you get your 20 points? The masses are stuck together, right? What else?
You didn't account for the conservational mass.
Yeah, I mean, there is a collision. Work energy is good, but it's, not as general. So it's not a difficult problem, but if you don't remember these, if you don't understand what entails a collision, when energy is conserved, and why, and you only did problems, you look at this problem and it's work energy problem, but it's not. This is not correct. Energy, it's a little bit more complicated. We have indeed 3 states to consider. The first state where we release the system from, second state, the collision, right? And then the third state when the spring is fully compressed. So then, I just said that when we have springs, what do we do with the system? We try to include the spring. So if we do a free body diagram with the springs, what do we see in the x direction? There is conservation of linear momentum. There is no force, no external force. The internal forces don't contribute to the momentum of the system. So this is really great, because when we identify that, when we notice that, okay, work energy is not how it works, so I need more equations, or I need to do something else. Now, if you remember when momentum is conserved and how the internal forces, the concept of an internal force not contributing to momentum, then the problem is easy. But if you start thinking, oh, but there's a spring force, so what do I do there with the momentum? I need to integrate. Where is the time? And it becomes, then there's where you lose your time. So I have three states. I'm going to go to state 1 to state 2 right before collision. So that's 2 minus. So you already have that. You know, the kinetic energy, initial energy is the same. Right before the collision, there is no non-conservative work still. And then after collision, right before the collision, my ball has gained, my particle has gained some kinetic energy, and the spring is still not compressed, so I have no potential energy in my system. So this is our happy state of affairs, in which we have simple equation, and we get that the speed in state 2 is just this, right? Masses cancel out. All right, now during impact, we use linear impulse momentum. Essentially, we are calculating how did the speed change due to the impact. So that is what I called state 2 plus, after impact, or let's say consider before impact, after impact. So linear impulse momentum equation, this guy is 0. Whenever we get rid of an integral, we are, you know, I like integrals, but I'm pretty sure most of you don't. So we're happier. And then we get here MP, the speed before collision. It's equals now, after collision, the two masses are together. And this is what we missed from doing the work energy from the beginning to state 3. So here we get that the speed after impact, it's equals to the ratio between the mass before being glued and after being glued. It's the other way around, sorry. Oh, yeah. I was doing it correct, sorry. So I have a reduction in the mass, in the speed, because the mass is greater. And this is our equation number, okay, this was 1, this is 2. And with that, then we can go from state 2 plus to state 3. So at state 2 plus, we have this. Don't forget the mass of the block. That sometimes happens, sorry. The potential energy in state 2 plus is still 0, because that we have touched the block, but we have not started compressing. So there is no energy stored in the spring. And then in state 3 is where maximum compression happens. So remember, that means that we have no more energy. All the kinetic energy became potential energy. And all that potential energy is over here on the spring. And then it's still not a difficult problem, because in the end, bless you. In the end, it's still a simple equation. that yields us the maximum compression. But we have to be a little careful and not forget that when we have collisions, energy is not conserved. That's essentially the point. So this problem illustrates nicely. I gave you two examples of problems that where the extra equations come not from kinematics, but from using combined, and this is going to be a big theme, combine linear impulse momentum and work energy. Let me just finish this. In the exam, it's not going to be clear for you which one to use. So it's very rare, the case in which to find the final answer of the problem, you have to combine work energy with Newton's second law and linear impulse momentum. Typically, you do, because with Newton's second law, you find forces and accelerations. Whereas with work energy and linear impulse momentum, you are comparing speeds and changes in position. So they two work together quite nicely, all right? And then to identify whether you need to use linear impulse momentum or not, look for internal relative motions in your system. Have a good day.